Hi, my name is Kirk Grundle, and I'm one of the support staff for the National Framers Council. We're going to give you a bit of an overview today of FrameSAFE and ad hoc testing that we undertook at the Structural Building Component Research Institute that was intended to really provide a foundation for taking a look at fall protection and how we can improve fall protection. The goal of testing is to understand load paths and wrap engineering around the needs of the framer. Ultimately, we want all of the framers that are on the job site to be able to do their jobs safely, to have appropriate fall protection devices, and we can only really do that well if we have a good understanding of what it takes to resist loads, particularly during a fall. As we got into this, we took a look at setting up an assembly of trusses, properly braced, and we ended up dropping a 250-pound weight through 6 feet. We conducted 4 tests of this type with different orientations of the weight in relationship to the assembly to determine exactly what kind of forces we were going to get through this kind of fall effect. Our ultimate goal, obviously, is to improve over time how we undertake attachment of trusses to fall protection devices and exactly the effect on trusses of a fall. The assembly looked like this. We set up 4 trusses, again braced to BCSI. We have lateral restraint and diagonal bracing. We also have 45-degree braces on the back side of the assembly to monitor loads that flow into those diagonal braces as you load up the truss with a 250-pound weight falling through 6 feet. The trusses are also sitting on load cells, so all the gravity loads will be measured as well. The assembly looks like this. The blue devices are the load cells that each truss is sitting on. And you can see the bracing, the lateral brace along the top and the diagonal braces on both the top chord and the bottom chord. And as a consequence of that, the bracing is holding the assembly stable. And then we've added load cells at the backside in the 45-degree angle members with load cells internal to those particular 2x4s so we can measure compression and tension loads accurately. You'll notice the load cells right in the center of that 2x4 cut into the 2x4. This is another example of that particular load cell. And so as we go through this process, we're going to use this information to understand as we load a truss up with a fall, how does that load transfer through the assembly? Back in 2009, we ended up working with NIOSH to do some fall protection testing on a full roof truss assembly, similar to this, but not with all the load cell devices laterally that we have here today. But the initial testing that we did just to get a sense for how load cells perform when a drop occurs from a fall type activity, we dropped a 60-pound weight through about 6 feet. And we wanted to see exactly what that would do to the double top plate kind of 2x4 setup and 2 load cells. That looks like this. There's a couple things you'll instantaneously notice. It's an impact load that happens very rapidly. The total load on the load cells is 2,112 pounds. Did not affect the 2x4 at all. You'll notice too that that decay rate happens very rapidly. And as a consequence of that, the physics says that there's a very high load under an impact kind of condition, but the actual load is probably more in the 100 to 150 pound range from the fall itself. And that initial impact is not something you want to experience, but nevertheless, it's a very short duration type load. And that should be able to be managed properly through fall protection devices like shock absorber lanyards and things like that. And that's proven to be the case, which we'll see in the next series of tests. Now this is the assembly test with the 4 trusses properly braced. This drop is right straight down between the trusses where the lanyard is attached to the peak of the truss, and it's the second truss in from the back side. The total maximum tension force from this drop is 119 pounds. The maximum compression force is 101 pounds. So it looks something like this. Now we also have a better view of that with a wide angle, and that looks like this. And you'll notice that there are measurements taken to make sure that we've got the drop consistently the same in every situation. So this will give you a sense for kind of our first test in a broader way, and take a look at the motion in the truss as we undertake this test. You notice that there's not much motion there at all in the trusses itself. The trusses are stable. Obviously, it doesn't make some sense that there's not much motion when the drop is straight down through the trusses. So given all of that, we changed the setup to now pull the load outside the truss assembly itself. I'll load up diagonally to that same connection, the second truss in at the peak. And what is going to happen to the assembly in this particular case? Here the maximum tension force was 376 pounds and the maximum compression force was 166. And again, watch the assembly and watch the drop and watch the shock absorber, as everything really tells a nice story when you can see it live. One thing you'll notice there is the trusses moved a little bit, but not very much in the scheme of things. So as we go through this process, we ended up having the group say, well, why don't we pull the lanyard over the top of all of the trusses, then drop the load, and the expectation of the group was that the load, because of the fulcrum effect, was going to be higher on the load cells behind and probably have a bigger impact on the trusses and maybe even break the trusses. And what you'll see here is a performance that was really quite interesting given the expectation. Now you notice that the two examples, or the two views of that particular fall, showed that the lanyard and the shock absorber extended much further. So the drop was, there was much more of a force at the corner of the truss, but there's also greater load distribution. And actually the load, the max tension load, was reduced in about half. And so from that vantage point, it's pretty clear that this particular drop, given the forces in the corner and how much the lanyard extended from the shock absorption point of view, the truss assembly obviously distributed the loads from the fall across multiple fasteners, reducing the load to the backside load cells, and the load distribution changed dramatically. So then we said, let's take the bracing off the bottom cord, so you'll see the diagonal braces are not on the bottom cord any longer, and do the drop again at the diagonal, which is the worst case load condition, and see what happens here. The issue that we may run into, and that we expected to potentially run into, is the fall, the 6-foot fall, could potentially cause the bottom cord to at least move, but potentially break, as the fall and the lanyards hits the bottom cord on the leading edge without the diagonal bracing. But you will see the effect of diagonal bracing. So did you notice the bottom chord move pretty dramatically? We'll do that again just to take a look at it one more time, because it does show the movement of the bottom chord without the diagonal bracing, but it does not break the bottom chord. The load was about the same, 381 pounds, so I think we had 376 pounds previously in tension. So not much change there, just a little bit more movement. So the point of all this is that a properly braced system obviously holds load. Now this is not a 60-foot set of trusses, it's a 30-foot set of trusses, but nevertheless, it begins to provide us with some insights we wouldn't otherwise have. And our goal with all of this is, obviously, if we can get more data and apply the data to engineering models, we can begin to design fall protection that's both safe and allow the structure to be put up efficiently, because we can design fall protection into an efficient application of trusses. So we have done quite a bit of testing in the past. A couple of assemblies that we've used to undertake load path tests look like this. You can see that this assembly is on load cells. We can measure all the load throughout this entire assembly. On the back side of that particular assembly is a girder truss. And we did use this particular assembly with NIOSH in 2009 for some preliminary tests as well, and some preliminary modeling. This is another example of the same, or another view of the same truss assembly. You can see the actuator right in the center of that assembly. We're applying loads there to understand load path through this assembly. And finally, we actually installed a KB roof system and loaded this particular assembly up to about 140,000 pounds and broke it. And we repaired those trusses and broke it again just to see the load distribution. But you notice we have load cells throughout this particular assembly. We've got load cells and web members. At the lower end of this particular assembly is a glulam beam right here, and that's on a fairly large load cell. So we're understanding load distribution throughout an entire roof system that's a fairly complicated roof system. So we can take all this information, put it into a SAP 2000 three-dimensional model, and actually see load paths. Well, what does this mean for the Framers Council and framing in general? We believe that if we can get information like this, and we've got engineering models that are fairly sophisticated, we can begin to optimize the safety on a job site by modeling the installation of trusses, modeling the fall protection, and making the entire process efficient and safe. Obviously, the only constraint on all of this is having the resources to do so, but ultimately, with the framers being engaged in these kinds of activities, we need to take their common sense that they use every day to build structures, and we need to begin to wrap engineering around that common sense. The ultimate goal, obviously, with the FrameSAFE program is to create a community that really wants to get this job done. The mission is to develop a series of best practices. Obviously, we've started that with FrameSAFE version 1, leading to version 2. And we're moving forward with continued feedback and continued use of that program and evolving that program appropriately to create a series of best practices and standards that, should all framers begin to use this, there'll be consistency across the board, and via consistency, it's more assured that safety will be part of the culture of framing. And ultimately, we want all framers to work safely and obviously go home at night back to their families in a safe manner. So thank you very much for listening to this. We're very excited about the future, and if there's any questions, certainly give we at staff at the Framers Council a call, and we'd love to help in whatever way we can. And if you need any further information, please call 24/7. Thank you. Bye-bye.